Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is your instructor Anisa Nawaz from Department of Physics. This is our lecture number 22 from chapter number 2, Vectors and Equilibrium. In the previous lecture we have discussed about concurrent forces, equilibrium force and moment of a couple. After listening to today's lecture, you would be able to explain the concept of equilibrium, types of equilibrium, and two conditions of equilibrium. So, first let's discuss what is equilibrium. We can define equilibrium as it is a state of body in which, under the action of several forces and torques acting together, there is no change in translational motion as well as rotational motion is called equilibrium. It means that if the body is in state of rest, it will remain as it is. There will be no linear acceleration or there will be no rotational acceleration. And if the body is moving with constant velocity, there will be no change in velocity, there will be no acceleration produced even if forces and torques are acting on that body. Okay, so we will say that under the action of several forces and torques acting together, there is no change in translational motion as well as rotational motion. This is known as equilibrium. Okay, so an object is in equilibrium when there is no net force acting on the object. Net force means that there may be some forces but their resultant must be zero. And there is no net torque. It means that torques may be acting on the body but the sum of all those torques must be zero. In other words, the object is not experiencing linear acceleration or rotational acceleration. Then the body is said to be in equilibrium. And the study of objects in equilibrium is called statics. Those objects which are in equilibrium, they are studied under the branch statics. Okay, we are having two types of equilibrium. First one is static equilibrium and second one is dynamic equilibrium. Dynamic equilibrium can be subdivided into two further types. First one is dynamic translational equilibrium and second one is dynamic rotational equilibrium. So first let's discuss what is static equilibrium. When a body is at rest under the action of several forces acting together, the body is said to be in static equilibrium. Okay, if the body is not moving, even certain forces are being applied on that body, still the body is at rest, then what we will say, the body is in state of static equilibrium. For example, a book resting on the table. You can see that if we are having a book, let's say it is lying on the table, and you can see that what is the force which is applied on this book. The one force is its weight. The weight is acting downward. Other force is the normal force, the reaction force which is being applied on the book by the table. These two forces are applied on the book, still the book is lying on the table, it is stationary, it is not moving, it is at rest. So we will say that this book is at rest under the action of several forces, so it is in the state of static equilibrium. And if we consider this book and we are applying force on this book and it is not at rest, then what will happen? We will say it is not in the state of equilibrium, okay, because it is changing its position under the action of force. So we will say that it is not in equilibrium. Okay, so an object is in static equilibrium when it is not moving. Any object which is not moving, obviously certain forces must be applied on that object, weight of that object and normal reaction must be there. So we will say that an object when it is not moving, it is in the state of static equilibrium. its velocity is 0 and its acceleration is 0. Okay, when the body is in state of static equilibrium, its velocity as well as acceleration are 0. So the body must be in translational equilibrium, or the body does not accelerate along any line. Okay, there must be translational equilibrium, no acceleration should be there. And if the acceleration is 0, then the resultant of the forces acting on the body is also 0. You can see again, if a block is lying on this table, then we will say that it is in state of static equilibrium, because there is no velocity and no acceleration produced in this block. For example, we are having this body which is placed over here. What is there? We are having weight W is equal to mg, which is 20 newtons, and normal force, again it is 20 newton. So both forces are equal and opposite to each other. They will cancel the effect of each other, and body will be in state of static equilibrium because it is at rest. Okay, so over here again same case, the body is present over here. Tension T1 is 10 Newton, T2 is 10 Newton, and weight acting downward is 20 Newton. So the forces which are acting in upward direction are equal and opposite to that of downward direction. So these two forces will cancel the effect of each other, and the body will be at rest under the action of certain forces. So it will be in state of static equilibrium because the body is not moving. Okay. Second type is dynamic equilibrium. When a body is moving at uniform velocity under the action of several forces acting together, the body is said to be in dynamic equilibrium. So what we will say that we are having a body which is moving at uniform velocity. There is no acceleration produced, there is no change in velocity under the action of several forces. So what we will say that the body is said to be in dynamic equilibrium. An object is in dynamic equilibrium when it is moving with constant linear velocity and or rotating with constant angular velocity. Okay, so it may be moving, it may be having translational motion, or it may be having a rotational motion. Okay, so both cases are for dynamic equilibrium. For example, when a body is moving with uniform linear velocity, the body is said to be in dynamic translational equilibrium. Okay, this is first subtype of dynamic equilibrium, that when a body is moving with uniform linear velocity, the body is said to be in dynamic translational equilibrium. For example, a paratrooper falling down with constant velocity. Okay, if a paratrooper is falling down with constant velocity, there is no acceleration produced. Okay, it is moving, but it is moving with uniform linear velocity. So we will say that the paratrooper is in state of dynamic translational equilibrium. Okay, so if we are talking about the second subtype of dynamic equilibrium, which is dynamic rotational equilibrium. When a body is moving with uniform angular velocity, the body is said to be in dynamic rotational equilibrium. Okay, so it means that there is a rotation. The body is moving with uniform angular velocity, it is rotating with uniform velocity, then the body is said to be in dynamic rotational equilibrium. For example, a CD rotating in CD player with constant angular velocity, that will be in state of dynamic rotational equilibrium. A ball rotating with constant angular velocity, you can see here that this ball is rotating with constant angular velocity. There is no acceleration produced, its speed is nor increasing or neither decreasing. Okay, so we will say that there is no acceleration, no angular acceleration produced. So it is in state of dynamic rotational equilibrium. Okay, the ball is in state of dynamic rotational equilibrium because it is rotating with constant angular velocity. So for example, if we are having this disc, okay, and if we see that this disc is rotating with constant angular velocity, we will say that it is in state of dynamic rotational equilibrium. It is rotating with constant velocity. It is in state of dynamic rotational equilibrium. But if we say that it is linearly moving with uniform velocity, then we will say that it is in state of dynamic translational equilibrium. Okay, and right now it is static, it is stationary, so we will say that it is now in state of static equilibrium. So now if we discuss about conditions of equilibrium, we are basically having two conditions of equilibrium. Okay, so for a body to be in complete equilibrium, it must fulfill two conditions of equilibrium. Okay, and what are those conditions? Let's check it out. The first condition of equilibrium. What is the first condition of equilibrium? It states that if the vector sum of all forces acting concurrently on a body is equal to 0, then the first condition of equilibrium is satisfied. If the vector sum of all the forces, because forces are vectored, their direction is also there, not only magnitude but their direction must also be considered. So if the vector sum of all the forces acting on a body is equal to 0, then the first condition of equilibrium is satisfied and the body must be in static equilibrium. For first condition of equilibrium, we must have static equilibrium. Okay, so if we talk about mathematical form of static equilibrium, let's say that we are having different forces which are acting on a body, F1, F2, F3 up to so on Fn. Then what should be there? Sum of all these forces must be equal to 0, because by definition we said that the vector sum of all the forces acting on a body must be 0. So this is the mathematical form. F net is equal to F1 plus F2 plus up to so on Fn is equal to 0. We can write it in the form of summation as well. If we say that we are writing this F1 plus F2 plus F3 up to so on, we can write it as summation. This is the symbol of summation, summation Fi such that I is equal to 1 to I is equal to n. Okay, summation sign means that if we are going to expand this force, we can write this F1 in this form. If we can write it as F1 plus F2 plus F3, and up to which point we will start from I is equal to 1 and we will end it at I is equal to n. Okay, I is equal to 1 to I is equal to n. Let's say we are having 4 forces, so we will write it as summation Fi, I is equal to 1 to I is equal to 4, and we will expand it like F1 plus F2 plus F3 plus F4. Okay, so this is the short form, this is the summation form of this whole sum. So we can write it as summation Fi is equal to F net, which is equal to 0. So this is the mathematical form of first condition of equilibrium, that sum of all the forces must be 0. Okay, and sum of x and y components of the force must also be 0. Okay, if we are individually calculating the x and y components, their sum must also be 0. We know that we can write Fr, resultant force, as sum of x components I hat plus sum of y components j hat. In component form we can write resultant force in this form. Okay, summation Fx I hat plus summation Fy j hat. And for satisfaction of first condition of equilibrium, summation Fx I hat, sum of all the x components of forces must be equal to 0, and sum of all the y components of the forces must be 0. Okay, so sum of x and y components individually must also be 0 for satisfaction of first condition of equilibrium. You can see this is again example of first condition of equilibrium. You can see tension T is acting in the upward direction, and gravitational force is acting in the downward direction, which is basically the weight. So due to these two forces, we say that the body is in equilibrium and it is satisfying the first condition of equilibrium. That's why it is not having any linear acceleration. F net is equal to 0. Sum of all the forces is equal to 0 because upward force is equal and opposite to the downward force. So what we can say? We can say that first condition, net force is equal to 0. Sum of all the forces must be 0. X component of the force must cancel each other. Summation Fx must be 0 and summation Fy must be 0. Okay. Summation F is 0, summation Fx is 0 and summation Fy is 0, and all are in vector form. You can see over here, if we are having different forces, let's say F1, F2, F3, F4, 5, okay, F1, F2, F3, F4 and F5. 5 forces are acting, let's say, on a single body, okay, and we want to check out what is their vector sum. What we will do, we will apply head to tail rule and we will add all these forces. You can see over here, if we are going to apply the head to tail rule, it is forming a closed figure, okay, a closed polygon is there. F1, F2, F3, F4 and F5. We are just obeying the head to tail rule and we see that over here we are having a closed polygon. So what will happen over here? This means that the resultant is a null vector. Sum of all the forces is giving us a null vector. This shows that the body will be in equilibrium. These forces, if they are acting on a single body, then that body will be in equilibrium because it is satisfying the first condition of equilibrium, okay. So there will be no linear acceleration produced in the body. So whenever there is a closed figure formed, it means that the resultant force is a null vector and the body is in equilibrium. Okay, you can see all these bodies are in equilibrium because the sum of all the forces is 0 and they are in the state of static equilibrium. They are not moving. So we will say that first condition is satisfied in the case of these bodies. Okay, how you can see that if you are having same body in which we are having normal force 20 Newton and mg acting in the downward direction, which is 20 Newton. You can see over here, if we are checking out the sum of x components, summation fx, there is no force acting along x-axis. So sum of all the forces acting along x-axis is 0. And if you want to check out sum of all the forces acting along y-axis, you can see that if you write sum of all the forces acting along y-axis, we are having normal force acting upward, so we will take it positive, and we are having weight acting downward, so we will take it as negative. N minus mg is equal to 0. You can see over here, N is 20 Newton, mg is 20 Newton, so 20 Newton minus 20 Newton is equal to 0. So it is satisfying first condition of equilibrium, that sum of all the forces is 0 and sum of x and y components of the forces is also 0. Okay, same is the case over here. We are having a body on which different forces are acting. There is no force acting along x-axis, so sum of all the forces acting along x-axis is 0, and sum of all the forces acting along y-axis, you can see T1 plus T2 minus W, okay, minus weight. So 10 plus 10 minus 20, that will give us a result 0. Okay, upward forces are taken by convention, they are taken as positive, and downward forces by convention are taken as negative. The second condition of equilibrium. What about the second condition of equilibrium? Okay, so according to second condition of equilibrium, if the vector sum of all the torques acting on the body is equal to 0, then the second condition of equilibrium is satisfied. In first condition, we are talking about force and linear acceleration, okay, and in second condition we talk about torque and angular acceleration. So body must be in rotational equilibrium. Okay, it must be rotating with some constant angular velocity. Mathematical form of second condition of equilibrium is tau net. It means that sum of all the torques acting on a body must be 0. Tau 1 plus tau 2 plus tau 3 up to so on, tau n is equal to 0. Okay, we are taking summation of all the torques acting on a body, that must be 0. Okay, or we can write it in the form of summation tau I, where I is equal to 1 to I is equal to n, which is equal to tau net, which is equal to 0. So sum of all the torques acting on a body must be 0 to fulfill second condition of equilibrium. Okay, so it means that for second condition of equilibrium to be satisfied, sum of clockwise torques must be equal to sum of anti-clockwise torques. Over here you can see that this body is having weight in the downward direction, and if we take this central point as pivot point, so it is having a clockwise torque, and this is again in downward direction, but with reference to this central point it is in anti-clockwise direction. So we can say that sum of clockwise torque must be equal to sum of anti-clockwise torque for the body to be in a rotational equilibrium. Sum of clockwise torque must be equal to sum of anti-clockwise torque. So when an object is in rotational equilibrium, the net torque applied to it is 0. Okay, you can see if the body is in equilibrium, so this, let's say this bridge is in equilibrium, it is not having tendency to rotate, so sum of all the torques acting on it must be 0, or in other words, sum of clockwise torques must be equal to sum of anti-clockwise torques. Okay, so what we have discussed, that when an object is in rotational equilibrium, the net torque applied to it is 0. For example, if an object such as seesaw is not rotating, you can see if it is not rotating, you know that the torque on each side is balanced, and if torque is not balanced, then what will happen, it will keep on rotating, it will be having the tendency of rotating. Okay, so for the body to satisfy second condition of equilibrium, the torques acting on each side of the body must be equal. Okay, so sum of clockwise torque must be equal to sum of anti-clockwise torque. So for complete equilibrium, an object to be in complete equilibrium, both conditions of equilibrium must be satisfied. There is no net force, okay, F net must be 0, and there is no net torque acting on the object, tau net is equal to 0. So there will be no linear acceleration, there will be no rotational acceleration, because sometimes what happens that a body is in it's satisfying the first condition of equilibrium, but still it is not in complete equilibrium. Okay, for example, we have considered the example of couple. So in couple, if we consider that sum of all the forces is 0, but still the object is rotating. Why the object is rotating? Because sum of all the torques is not 0 in the case of a couple. So we will say that for a body to be in complete equilibrium, first condition as well as second condition must be satisfied. Okay, without that the body cannot be in complete equilibrium. It will be having a tendency to move in some direction, or to, if only first condition is satisfied, then the body may be rotating. If only second condition is satisfied, then the body may be having linear acceleration. Okay, so for complete equilibrium, both conditions must be satisfied. Okay, so I would like to end my lecture with this quote, that I'm just a child who has never grown up. I still keep asking these how and why questions. Occasionally I find an answer. Stephen Hawking. So you also have to follow this thing. Okay, we must ask questions. If we are not getting anything, if we are not understanding anything, then we have to ask these questions, how and why. This curiosity basically leads us to knowledge. That is a very important thing. Okay, so that was all for today's lecture. Thank you so much. Best of luck.